Okay, Michael, did you distribute the homework yesterday?
Yes, the homework has been distributed. They didn't even get the solution.
Okay, great. So are you finished with this? So can we get this over with? Not yet?
Not quite.
Not yet, no.
No, not yet. Okay, cool. So how's the screen? Do you see the introduction to ZAERO short presentation?
Yes, we do.
Do you see the slide? So can we start?
On your time.
Okay, so just technical note. For some reason I see several people with rest crossed out mics, and I am not able to unmute them. So I have no idea why, but maybe it's on your end, guys.
Yeah, some people may not have microphones.
Okay, so just a side note, I want this to be interactive. So in every point that you have a question, please ask, and I'll try my best to answer. So don't feel intimidated, even by the circumstances. Okay, let's start. My name is Danny, and I will show you a short presentation about ZAERO. ZAERO is a commercial Aeroelastic code. So in short, it's the answer to the question: what are you going to do when your structure is no longer a plate or a beam, but say an F-16, like here. So the first question is, what are you going to do? For example, if you have a plane and you want to find the Flutter boundaries of the structure. So guys, chime in. So just throw your answers. Guys.
I will run an FE code.
Sorry?
I will run an FE code.
That's right. So usually what we do in the industry and all places outside academia, we use finite element code. That's completely true. And ZAERO is one of these codes that is suitable for aeroelastic analysis. So we'll start with what is ZAERO, and I'm going to show you some examples from their marketing material. They advertise themselves as engineering toolkit for elastic solutions. So all of these disciplines, whether it be unsteady aerodynamics, Flutter solution, nonlinear Flutter trim, or ejection loads, gas loads, and Aeroelasticity, can be all handled inside of this package. So in Aeroelasticity, no matter what you do, eventually you are going to solve this equation. I am sure you are all familiar with it. Is this true?
Yes.
Yeah, so left side is the structure, and the right side is the unsteady aerodynamics. And AIC is some designation by ZAERO, so we are going to proceed with it. We're going to talk more about this slightly later in several slides. Next slide is a little side note. So ZAERO were not the first to the scene of commercial aeroelastic products. Nastran were the first, and Nastran were developed with the federal funds in the 60s. And if you're familiar with the package, it's a huge finite element package that handles all kinds of disciplines. And yes, and each discipline has its own solution code. So our elastic solution is 144 through 146. I'm sure there are other disciplines that are supported now.
Is Nastran still used today?
Yeah, Nastran is a huge package that's used in US and worldwide, and it's a industry standard in NASA, in Boeing, for example, and in also I believe in Airbus. So yeah, it's really capable code, not just for aeroelasticity, also for general finite elements. Okay. And yeah. So in contrast, sorry, ZAERO is a small privately held company in Arizona. Which is Zona is ZAERO from Arizona. Whatever you might figure out from this. And yeah, so they started in 1985, and they offer pretty much the same capabilities of Nastran, but they're really enhanced their offering of software packages. And this is what I've been using for since 2005, maybe, in industry. So I'm not familiar with Nastran solution. I just know it exists, but ZAERO is very capable package, and I'm feeling very comfortable with flying an airplane that was designed with ZAERO solutions. So they are really connected to the real world with no caveats. Okay, so let's. This is a short slide for short comparison with Nastran with ZAERO. As you might see, ZAERO has more unsteady aerodynamic capabilities than Nastran. They only have a doublet lattice method and Zona 51, which is at supersonic aerodynamics, where ZAERO enhanced this for transonic and nonlinear hypersonic, and also for supersonic aerodynamics. Also, if you look at these two pictures, the geometric model of ZAERO is a lot nicer than these of Nastran. Nastran is just flat panels, and in ZAERO you can do body elements. You can give volume. You can add all these missiles and bombs, all the stores to your aircraft. And yeah, a really capable, really enhanced model of geometry. Okay, so far, any questions? I hear none. Okay, let's go on and just go over the reasons that I think that you should use ZAERO. So first of all, it's a completely engineering approach. So me as engineer, I don't want to deal with vector lengths inside of the code. I don't want to deal with compatible aerodynamic package. So I want to just specify the Mach number, and the program will choose the coefficients for me. So I don't want to deal with all the mechanics that is not in the engineering front. And ZAERO does this very nicely. It uses the model approach. The model approach is what you might learn as the using natural modes to describe your structure. And interestingly, it uses this also for static aeroelasticity. So it might seem counterintuitive, but it's totally fine to use this. And just think for a second, which discipline needs more modes provided? The Flutter solution or a static solution? What do you think? Guys?
Can you repeat the question, please? Sorry.
Yeah, so if I'm using the model approach, if I'm just describing my structure as a combination of linear natural modes, in what circumstances do I need to use more modes? With Flutter solution or for static solution?
For static solutions.
That's right. That's right. Why?
Because usually Flutter is fluttering in one specific mode.
That's right. So for dynamic results, you usually Flutter or dynamically accelerating at several modes, one or more. And for static, you need more modes to do a general combination of motion. This is correct. So Nastran doesn't do this. So for Nastran, if you want a static solution, for example, trim analysis, you will need to provide the whole model, and it's a huge quantities of nodes and unnecessary information. Also, one of the powerful points that ZAERO uses, it can accept model data from any finite element code or test for this matter. And Nastran uses only solutions that were generated by Nastran. So it does not limit me to any particular package, or for example, if I want to get my model data from test, I can totally do this, and ZAERO runs with no hiccups with this. The aerodynamic model. So once it's unified, they call it unified aerodynamic model. What it means simply is that once I generate my grid, my aerodynamic box grid, I don't need to change it for different Mach numbers. The coefficients inside will be different, but the model is generated only once. And this is also saves a lot of time. And it uses the cards approach, and we'll talk about this a little later. Also, it has really good manuals, and you will use some of them in your homework. Now, the bad might be no user interface. Sorry, guys. So ZAERO is just text in, text out, and it's cards approach. So cards approach, we will see what it means, and beginner users find it cumbersome, maybe not so user friendly, and they're completely right. But we have nothing to do. We can do nothing about it, so we're stuck with it. Okay. Now let's talk about what we're solving. So, any questions so far? Just bureaucracy so far. Any questions before we proceed?
I don't know if you're going to cover this afterwards, but what's the efficiency of ZAERO versus Nastran? Is it faster or about the same speed to solve?
Well, I have no idea.
Okay.
I have no idea. Both of them are linear codes, and it depends, of course, on the size of the model. What I want to say is that in industry, you don't easily change what works. So, for example, Boeing, they might be using Nastran for the last 30, 40 years. So to offer them a package that might offer some of the advantages against something that they know that works might be very, very challenging task. So those that use Nastran, they will probably continue using Nastran in the foreseeable future, and vice versa. So I don't think that there are many test cases that are comparing directly runtimes between the two programs.
Okay.
That happening now. Anything else? Okay, let's go on. So let's talk about the equation that we solve and in every discipline in our elastic analysis. So for left-hand side is our structural model. It can come from finite elements or model test. Those of you who were at my presentation in advanced vibrations saw the demonstration of model test. This side is provided as model data. So model data are generated masses, natural frequencies, and natural modes. That's it. We don't need the physical matrices. For right-hand side, we generate this inside of ZAERO, and it depends on several conditions. So it's a flat condition, gust loads, maneuvers or static loads, and of course control commands. All of these can be accounted for in this matrix, or maybe in several others. Okay, so next question is what is a good structural model, structural finite element model? More specifically, if you have F16, for example, what are your specific actions to generate a good finite element model for the aeroelastic analysis?
simplify the geometry.
Okay, how so?
I don't know. For example, like yeah, like you don't need all the kind of internal details to
That's
focus
right.
on, like
It-
the external structure,
Mhm.
and if you have symmetry, for example, also.
Okay. Who am I talking to? Who is this?
Jan
Okay.
Jan
Yeah.
Reyes.
You appears to be answering all the questions, so at least I know your name now. Okay, so the question is, when you're talking about finite elements, are you thinking about this? So very detailed model with generated stresses at the ribs and the beams. So were you thinking about something like this?
Me or someone else?
All of you. My question is this your association with finite element model?
This is Matthew, and yes.
Okay. So the answer is during the development process of aircraft or anything for that matter, there are several models that are built during this process. So this model might be very, very good to find out the particular stresses in the particular ribs. And it's very detailed and very nicely built. But for aeroelastic analysis, we only need stiffness and mass. So this model is totally sufficient for our purposes. So if you want to generalize the fuselage as beams and use concentrated masses as all the internals, is totally fine. And yeah, so it looks really, really awkward for non-structural guys. And usually this model is harder to build than very, very complicated finite element model, but it saves you a lot of time and the sizes of your model. And yeah, so this when we talk about structural model that is suitable for aeroelastic analysis, we're talking about this very, very condensed model with beam and shell-like structures, elements, sorry. So for our purposes, we can build only half of the model. And it's totally fine for approximately 99% of the cases. So why is this so? Why is this the case? Why can we get by with only half of the model?
Because of symmetry.
Okay, yeah, because of symmetry, and if we're talking about aircraft, we can roughly divide all the natural modes by symmetric and antisymmetric modes, both of which can be calculated with only half of the model. And ZAERO supports this, so it only asks you to provide only half of the model. So we talked about this before, but we provide only the model matrices inside, and we can really reduce the size of the model by doing so. So before we show you an example of size reduction, when you might need the full matrices, what are the cases when you might need full matrices and not the model ones?
If you have a very unsymmetric plane or something that you're analyzing where you're going to need different matrices on each side.
Well, yes, but if you need if the two sides are not symmetric, you can just expand your model to both sides and run the full analysis and still provide the model matrices.
How about an unsteady case?
Sorry?
Like, do we need that in an unsteady case in which we cannot do a modal analysis, but we need to go in a time domain?
Well, no. Usually your aeroelastic analysis is done in the frequency domain. That's why you usually provide the model matrices. Okay, so one of the reasons when you might need the full matrices is for example, for aero servo elastic analysis. When you have control commands So if you have a control surface and it does the command, like let's say angle of attack, you need to know the mass of the surface and the inertia. So that's one of the reasons that you might provide the full matrices for the code to know what mass the surface might have. Okay, so one of the reasons. So with this model, it's just a short example how you can reduce your model by going model by going to the generalized masses. So we have 744 grid points with 6 degrees of freedom at each point. We have 4,500 degrees of freedom for the whole model. So your matrices, mass and stiffness, will be 4,500 by 4,500. And if you're using only 15 natural modes, your matrices reduced to 15 by 15. So it's a lot less work for you and for the code. Okay, questions so far?
Yes, I have a question.
Yeah.
So in this slide, what you write here is a 744 times 6 degree of freedom. What is this result? 4,464. Is that the magnitude of the matrix?
This is, yeah, so this is the total degrees of freedom in this model.
Ah, okay, I see.
Okay.
Yes,
So
thank you.
your matrices will be this by this. So they're square matrices.
Thank you.
Okay.
I have another question. How do you
Yes.
obtain this stick model of the airplane? Do you use semi-monocoque structures or something like that?
Can you repeat the question?
I was wondering how can you obtain this stick model of the airplane? Do you use semi-monocoque structures and stuff like that?
Oh, no, the question should be in reverse. So given your monocoque structure, how do you do this beam element, right?
Yeah.
So beam elements can be generated for any structure. Beam element, the formulation is this. So you have the beam. It's usually 2 nodes, and you provide the moment of inertia and the cross section. So if you can get those from your, for example, from your CAD model, this beam will represent your fuselage just fine. Of course, with the limitation, it will be only in bending and maybe in torsion, and that's it. You won't get any localized stresses from this model. Okay, was this good?
Yeah, it was good. Thank you.
Okay, thank you. So we discussed the finite element model, and another ways to get your natural modes is by doing a test for an actual structure. And yeah, so we did a short demonstration during advanced vibrations, but this test can for large aircraft can run for several weeks, and in the end you have a nice model representation of your airframe. So the test involves exciting the structure and recording the results, and in the end the outcome of this test can be used in ZAERO, for example, for aeroelastic analysis. And in this way you don't need to build your model. You're obtaining it directly. You don't need, for example, to turn your model into a stick beam figure. You're obtaining this directly by this test. Okay. So just a side note, if you have during your career to participate in such a test, do it. It's really rewarding. Questions so far? Okay, we talked about the structural model. Now let's talk about the aerodynamic model. And the first thing that we need to say is that aerodynamic model has nothing to do with the structural one. And this is totally the case. They're built completely separated. And why will this be good? Why do you think?
Because we can optimize the model for the two different calculations. So we're going to have the best mesh for the aerodynamics and the best mesh for the structure, and the talk time can be different.
That's one of the reasons. Yes. So aerodynamic mesh. Think about the refinement of your mesh. For aerodynamic purposes, the refinement will be, for example, at the wingtips. And if you're thinking about structure, nothing happens at the wingtips. That's exactly right. So the meshes, the models are different, and they serve different purposes. Other reason might be if you want to do a series of calculations with different for say structural models. You can generate only one aerodynamic model and then run several structural ones to compare your results. And this is completely seamless because the models are not connected. Okay, but not everything is very easy. So you as engineer have to make sense of your entire simulation, right? So the models can be 20 feet apart. It won't make sense. But you as the user has to make sense of where each of the models exist. Okay, so if we're talking about F16, this might be a typical aerodynamic model. You see, these are aerodynamic panels with body and all the stores under the wings and the surfaces. Any questions? So we talked about the aerodynamic model and the structural one. The fact that you can build them separately is because of the Spline model. The Spline model inside of ZAERO, it's a very powerful tool, which what it does, it ties the two models together. So you think about aerodynamic loads, for example, are generated in the aerodynamic model, and they need to be transferred to the structural one in order to obtain the correct deflections. And vice versa. If my model deflects, the aerodynamics will change. So the deflections have to be transferred to the aerodynamic model in order to obtain different angles of attack and to generate new aerodynamic loads. So this is a simple like flowchart of this model. The interesting thing that it's completely transparent to the user. You as the user just say to ZAERO what are my structural grid points, what are my aerodynamic grid points, and the G metrics will be generated inside, and there are no really hard limitations on this. So it's a very powerful tool, and it makes our life really easy. So the example of this is here. So you see aerodynamic model and structural one, and you see that the deflection, for example, it's pitching up. Also my structural model pitching up, and also wing bends here, and the same goes here. So this transfer between the models occurs with the spline metrics. Any questions? Okay, so once you realize this, you can really have fun with ZAERO. You can build whatever you want, and just several points. So wings are flat plates. We can introduce airfoils, but they are active only for supersonic flows and for nonlinear corrections. Span-wise divisions have to be parallel to the flow to the x-axis. There are several limitations of the vortex line. Simply what it means that the shed vortex from upstream surface, for example, for the wing, cannot cross in the middle of the aerodynamic box. So the lines, the division lines of the wing and the rear stabilizer in this example, for example, they need to be aligned. But this is very simple to achieve. Wing body interface, and we realized this really easy. So you might think that the aerodynamics in the transition between the wing and the body might be very complicated problem. But for the user, it's not. It's just a matter of specifying this wing is attached to this fuselage, and that's it. So the program will deal with the transition. And as I said before, same model goes for all Mach numbers. For example, I can use this mesh to generate aerodynamic coefficients for subsonic, supersonic, and hypersonic flow. It not necessarily makes sense, but you can do it. So questions so far?
Could this be adapted to somewhere where instead of air, it'd be water, say flow around a submarine underwater?
Well, you can do this. You can just specify different density of the flow. Yeah, it's totally linear, so it can work with either. So far I told you about all the advantages of ZAERO. Now we're going to talk about some of the maybe caveats. There are not a lot of them, but you will have to deal with them. So questions so far? None. Okay, so we'll begin with this. Who knows what this is? I hear Dr. Dowell in the background. I know that he knows what this is.
You have to be, I think you have to be over 50 years old to know what a punch card is.
I agree. Guys, any of the young ones? Young people
used to run simulations.
Sorry?
And it's how they used to run simulations and calculations through punch cards through a supercomputer.
Yeah, so this is this is the era prior the floppy disk. So this stack is an example how programs used to run. For example, you're taking this stack to your computer and imagine that you trip and this all goes flying in the hallway. So your day might be ruined after this. But that's how they did the calculation before. So why am I telling you this is because ZAERO has the digital version of this. So your inputs are looking like this. Each grid is called card, and it has 80 columns, and it is divided into 10 fields. And of course, you cannot go between the fields. The program will return error. You have to be inside of your field. Yes, you do a lot of spaces there, but that's how the program runs. So your input text file looks like this. So if you want someone to blame, you can blame Nastran because ZAERO entered the same market as Nastran was running this method. So yeah, we are stuck with this in the foreseeable future. Any questions? No. Okay, so I'm about to summarize my ZAERO presentation with additional highlights. So everything that you generate inside ZAERO can be exported for external use. You can export, for example, the aerodynamic matrix and use it in MATLAB. If you wish, you can do this. You can use your hardly obtained CFD or wind tunnel test data to fix the linear matrices of AIC matrices. There are dedicated cards that do this. You can modify your structure with a model approach. So yeah, ZAERO doesn't have a finite element engine inside, but you can do limited modifications with the model approach. You can generate results, and you can use any program of your choice to plot them or to view them. For example, Excel or TechPlot. ZAERO does not have any plotting capabilities. It's like it's text in, text out. And they are generous enough to add a nice VGplot tool that can plot your results. So when I say VGplot, I am sure that all of you know what this means, right?
Yes.
Okay. Except you, Michael?
Of course.
Okay. It's you again. Okay. Guys, do you know what VGplot is?
No.
Oh.
In theory, the students should be familiar with these. We covered them in the past couple of lectures.
Okay, VGplots. This is a VGplot. VGplot is a totally like widely accepted way to show aeroelastic analysis results. This is a typical one. VGplot is divided into two areas. This is the G area and this is the V area. Sorry, this is the So x-axis is your velocity in both of these plots. Vertical axis here is your natural frequencies. At zero velocity, these values are your natural frequencies. Okay, as you increase your velocity, your modes are changing. So you see that the trends are moving. Okay, and also when you increase your velocity, your aerodynamic damping is increasing or decreasing, and this is the vertical axis of the G. This is the G axis. So in aeroelasticity, it's really weird, I know, but negative means stable. Negative damping means stable. Okay, so this is one of the ways to show where flutter occurs. For example, let's follow this mode. This is the first torsion. You see, this is slightly decreasing, and while it decreases, it changes the damping from negative, which is stable, into positive. So this point is the flutter solution. Okay, and this is one of the ways to show the flutter results. This is widely accepted, and ZAERO just generates this plots. Okay, was this clear enough, or
does it provide the plots, or does it just provide the inputs that you can then go plot in MATLAB or something of your choice?
Yeah, it doesn't provide the plots. It provides the text column, text file for you to plot. For example, with the edit VGplot tool. But the plot is.
Danny, I have a question for
yes.
you. Could you show that plot again, the VG plot again?
This one.
Yeah.
Yes.
If you look at the frequency plot, the lowest frequency is first vertical bending,
Mm-hmm.
and the frequency seems to be going to zero at about not quite 300 meters per second. And normally when I see a frequency going to zero, I think divergence is about to occur. But then if I look on the left-hand side and I look at first vertical bending in terms of G versus velocity, it looks like there's still a very heavily damped mode. So what's happening there? Do you know?
Yeah. So who was this? Jeffrey? What was the question?
Well,
This is Dr. Dowell.
Oh, okay. So Dr. Dowell, this.
One of your students. Yeah.
The branch is here, so it goes down, and then it returns here. So you don't see all the damped portion down there.
Okay.
Okay, so it plunges here, and then it returns here to meet the frequency.
Okay. All right.
Okay, so it's still zero.
Okay.
Okay. Okay. Any other questions? Okay, guys, we are finished with the ZAERO presentation. Now we are going to. I will show you some I don't know bullets. What you are going to do in your homework. So this is the general Flutter procedure with ZAERO. And the way it's written here is, let's do all of them. This is what you do, and this is what ZAERO card is doing this. So you in your homework you're going to go through all of this. Okay, I don't want to read this because you all have this, and I would rather show you more specifically what you're going to do in your homework. So first question is, do you have any questions before we proceed? No.
Will you be sending out these slides?
Yeah, well,
these slides are actually already attached, I believe. If you look at assignment 11.
I think it's just the.
Oh, I did not include it. Okay, I will include the PDF of these slides in the resources under lecture notes.
Thank you.
Yep.
Yeah, so you'll have the PDF of the slides, and your homework it's also specified in the homework PDF, but you will need to use ZAERO to find the Flutter boundaries of this delta wing. Okay. So what we give for you is the model results. You have all this model data, and you're going to use ZAERO to answer these questions. Okay.
Danny, general question?
Yes.
How many modes do you tend to try to import into your FE model or into this from your FE model? Is there a general idea of how many modes, or is that really dependent on what your Flutter frequency might be?
So, there are several answers to this. The included file that you guys have includes 10 modes. 10 modes is just like default in ANSYS, so I just included them.
Mm-hmm.
But when you plot your VG plots, you will see how many modes are participating. So you might just throw away all the remaining ones.
Mm-hmm.
So in what I heard in industry, there are several practices. In Airbus, I believe they include all of the modes until 50 hertz, like for big aircraft.
Mm-hmm.
And this can be like hundreds of modes. Or I heard for another approach, they use the first 120 modes. So it's a mixed answer for this.
Okay.
Okay, guys, several tips.
Another question, please.
Yes.
What is matched and non-matched analysis?
Okay, it's a good question. Let's return for a second to our equation. So this is happening slowly. Okay, where is this? Okay, this is our aeroelastic equation. On the right-hand side, you have this AC, which is a matrix of aerodynamic coefficients, and this is the dynamic pressure. Non-matched analysis does the following. For example, you're looking for Flutter at Mach 0.5. Okay, so you're generating your matrix, your AIC matrix for Mach 0.5. And then your dynamic pressure changes independently. So you can totally run this from 0 meters per second until even 300, 400 meters per second. So these are not non-matched. This does not match this. In meshed analysis, these two are connected. So if you are generating this for Mach 0.5, your velocity should be at least physically attached to this. So why are we doing this? I tend to treat this like the non-matched analysis and the matched analysis. They answer different questions. The non-matched analysis answers the question: how far are you with your Flutter solution when you're flying at specific flight conditions? For example, if you're flying at Mach 0.5 and you are getting your Flutter solution at, for example, 500 meters per second, you know that you are safe. Okay, so this is you're calculating the margins directly.
Mm-hmm.
Matched point analysis, you're looking for the exact onset of the Flutter. You're looking for the exact point where your aircraft will flutter, which might be relevant or not. For if you're flying at Mach 0.5 and you're fluttering at Mach 1.6, it doesn't really matter. It doesn't really matter if you're fluttering there, as long as you're flying below it. So was this?
Yeah, that was fine. Yeah, I got it. Thanks.
So we usually start with non-matched because we see the ballpark of our analysis.
Okay.
Okay. So yeah, this is your wing. So guys, additional tips. This is what you have. The model results are in free format and they're metric. You can start with working examples. When you install your demo version of ZAERO, go to case 1. There is a working Flutter input. So change this according to what you need. And before you look at the results, go to the end of the output file and look that you can actually look at the results. Okay. And the manuals are really good. So you will probably consult several of them, and they're really good and elaborate.
Where is ZAERO located? Is it on the Duke computing cluster, or is it on Whitehead and Euler?
Okay, Michael, can you answer this? Michael?
Hello, sorry, is my mic working?
Yes.
Hello.
So, Michael, can you provide the ZAERO demo zip for the students?
Yes, that I can say confidently is attached to the assignment 11 that is on Sakai. The assignment itself, the docx file, as well as a zip archive holding all of the ZAERO demo install files.
Just install it on your local machine and just run it.
Michael, I'm sorry, I don't think it's there. Like, I only see 2 elements. One is the doc file, and another one is the txt file with the 10th mode of FE. I don't see any zip file.
Did it not attach? I waited about 30 minutes for it to attach before I posted the assignment. It doesn't look like it attached. Okay, I'll post that. Maybe the attachment was too big or something. I will reattach that. I'll put it in resources so you guys can find it. I'll put it in the I'll put it in lecture notes as well. I'm sorry about that, guys. I'll post that right away.
Thanks.
Yep.
Okay, guys, any questions?
Can you talk about what you've used ZAERO for your research?
Okay, for my research, I use ZAERO for the piezoelectric plate calculations.
Mm-hmm.
We had a fluttering plate that was equipped with piezoelectric elements, and we used ZAERO to find the flutter boundaries of this plate. I can actually show you this on Thursday. I can show you several movies of this plate if you want.
Perfect, thank you.
Okay, guys, just a side note. On Thursday, I'm going to give you the answers to this. So if you can finish this in the next couple of days, this will be all good. So it was part a joke, but I'm sure that you will need to provide the full solution, of course. besides the end answers. But yeah, on Thursday we'll have a lot of movies, and I will show you the Flutter test of this particular one. Okay, any questions so far about ZAERO or anything else?
General question: do we have lecture in this Thursday? Hello, can you hear me?
Dr. Dao?
I'm sorry, what was the question?
Do we have lecture in this Thursday? I thought the class will be in tomorrow, the graduate student class. I'm not sure.
So officially, graduate classes ended last Tuesday.
Did they? Okay.
And undergraduate classes officially end tomorrow.
Okay.
But we're providing several optional lectures for students to attend this Thursday and next week.
Okay, I see.
So this homework is part of the course. We encourage you to attend the lectures. We think that they're helpful, but of course we understand you have other class obligations you have to worry about as well.
Okay, anything else? Okay, thank you. I think I'll finish for today.
Okay, Danny, thank you so much. That was great. Thank you very much. And Michael, thank you as well.
Of course. So as a reminder to the students, this assignment, you've got a quick turnaround. This assignment is due Thursday before class by Danny's request. And we're going to have Thursday's lecture dedicated to discussing the solution to that homework, as well as some other details about ZAERO.
Well,
you're also going to see some experiments, some windfall experiments for the model that you're calculating, which I think will be interesting for you.
Yeah. So for I don't know. You'll have to talk to your TA about submitting the homework in 2 days. But this will be this might be the easiest homework that you had in this course. And you just at least have your solution for Thursday to check with the movies. So on Thursday I'm going to show you a lot of movies of Flutter and vibrating stuff. I hope you'll enjoy this.
Thank you, Danny.
Thank you, Danny.
I'm
Thank you.
Thank you.
Thank you, guys.